All right, so we left off on talking about the solar cycle and how the sunspots are cooler than their surroundings. I'd already mentioned that it was because of, what does it take, right? The darkness comes from where the peak of the black body spectrum is, and we also talked about the reason they're cooler because the magnetic field is causing the gases to be cooler. At least I know we started on that, but we'll be talking more about the magnetic field in just a moment. All right, that was just going to kind of be how we wrap things up here, talking about the sun's magnetic field. If you recall, I had said it was expected to be a very chaotic magnetic field. The way sometimes I think about it is you have the magnetic fields that are generated by terrestrial planets like ours, which is this almost like perfect dynamo system. It almost looks like an electromagnet in terms of being a really clean field that has a defined axis, and that axis seems to be, pretty closely associated with the rotation, which, really makes it feel like a dynamo because that's the idea is that you need rotation. Um, like that's how like we generate power, from like say like windmills and turning turbines, electrical power at least. So then you have the slightly messier magnetic fields that we see with the ice giants. So, with Uranus and Neptune, where they're not aligned with the actual rotational axis, they're not even centered at the center of the planet, and so they're kind of off kilter and off center, and the mechanism isn't entirely clear, but they definitely seem to be a little bit harder to pin down and, as I said, messier. And then finally, you've got the sun's magnetic field, which is just this totally dynamic system, always looping over on itself, literally tangling the field lines to the point that they actually snap, so to speak, and release huge amounts of energy. And so it's just the far end and the total opposite of a kind of stable, nice magnetic field like Earth has. And that magnetic field of the sun is has a lot of consequences. So, looking at black body radiation, black body curves, we've got a graph below that illustrates the curves for a normal region of the sun's photosphere and a sunspot. So, which is which? Which is the sunspot? The blue one, which is thumbs up, or the sorry, green. I'm not colorblind, just wrong word came out. The green one, which is thumbs up, or the blue one, which is thumbs down. Which corresponds to a sunspot? Okay, Maria says blue. Okay, cool. So seems to make sense. Okay, absolutely correct. I don't think that does the answer show up there? No, not really. So how do we know? Well, I'll paraphrase what comes to mind. One thing is the where the peak is. Okay. So we look at the location of the peak and it's in the infrared. That's why it appears dark. We also know that it's cooler, and we know that there's a relationship between intensity, which is one of the ways that this axis is represented, and intensity is going to be watts per square meter. So might as well put the units there. So watts per square meter. I say one of the ways because there actually are different ways that are going to be equivalent, different units that have the same relationship to wavelength. But with intensity, and you have this much lower curve. So you look at it and you say, oh well, look, not only is that peak where you would expect it to be in order to appear dark, um, but also it's going to be colder because you remember that the colder things are redder. And then to just really drive home the idea that it has to be colder is just the size of the peak because it's much smaller. So like the area under the curve is one way to think about this, but also just like the actual height of the peak, as I kind of showed with that dashed line. Well, that is going to be related to the temperature with that fourth order relationship. So the intensity is related to temperature raised to the fourth power. All right. So you have a really big uptick in intensity with a small change in temperature. So it need not be that much cooler in order for the intensity to be much higher. So all those things check out in terms of what we're looking at. Okay, much lower peak and move towards the right. Okay, skipping over that. All right, so an astronomer observes a set of sunspots forming a vertical line as shown to the right. Which of the images below shows how the sun would most likely appear a few days later? All right, so these are like three sunspots located on the sun, and then, okay, which of these is going to show where those, what the dots would look like 3 days later? I won't actually check the chat, so we can move on, but I will give you a moment to think about it and go ahead and answer it if you want, please. Okay, so this is the original state here at like, t equals 0, time equals 0. So is it this one here? Do they flip relative to the equator, like go from south to north? All move like uniformly as shown in 3, get spread out like in 4, or get spread out the opposite way like in 1, right? Because that's the difference. Okay, well, the answer is 1 because of that variable motion. The rotation at the equator is greater, so it doesn't move together, right? It's behaving like this fluid with separate regions moving faster than others. And the equatorial motion of the sun's surface is faster than the higher latitudes. Also, than the lower latitudes. The equatorial is the fastest. The sunspots there will disperse relative to the others because they are actually moving at a greater velocity across the surface. Their translational velocity. In fact, the rotational velocity is different as well. Um, so that's the idea of variable motion on the surface of the sun. The only part of the sun that moves as a rigid solid is the core. The whole surface moves with those variable motions. So this is the idea of differential rotation, same as with the gas giants. That's shown here. Okay. So essentially, the question before was, saying like, oh, could you connect the dots and, or make a reasonable guess? Because of course, this is you know, the clear case of spelling it out. You can see, right? They start aligned, just as an example, and then after some amount of time, the higher latitude sunspot lags behind because it has a slower velocity. You can actually look at the arrows that represent their variable or differential rotation. Those different motions can be tracked. So the surface moves faster at equatorial or at the equator and slower at the poles. This can be measured by sunspot motion. This idea of tracking sunspots as a way of finding values for the differential rotation is really similar to what we talked about for Jovian planets when we said that an astronomer would track a particular storm or feature in the clouds in order to find out the differential rotation. And the Jovian planets likewise are, have only the core moving as a rigid solid. So that's interesting because remember, they all have defined rotation rates, so does the sun for that matter. And that's always going to be in reference to the core. Even though, the surface is what we see, if we just want one number, we talk about the core and its rotation rate. Okay, so the solar cycle. So this is the cycle of sunspots on some level. So that's a great way to remember it and a great starting way to think about it. Because if it's the way you can directly document it, and it's the way it has been historically documented. So notice that the vertical axis is literally sunspot number. So it's just counting how many sunspots show up on the surface of the sun. We can see all sides of the sun because it rotates a lot faster than we orbit it. So it's not hard to get a full coverage or a full count. And in doing so, astronomers have since the year 1800 very accurately been counting the number of sunspots that are visible and found that there is a reliable cycle to this process. So the sunspots peak. They have a peak number of sunspots. They fall off until there is nearly 0 sunspots, which is a solar minimum. and then back up to a peak and back to a solar minimum over and over again. The period of this cycle, so how long it takes it to repeat, is, well, who can tell me looking at the graph? What is the approximate period of this cycle in years? Supposed to be a Y in parentheses. I'll erase it, make it a little bit more clear. So what is the approximate period? Looking at the graph, what do you see? 10 years? Yeah. 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 It's yeah, take another look, Maria, because 100 would be like, it would be something like that goes like this, right? That'd be like a 100-year cycle. So it's not a 100-year cycle, but it is about 10. And the more accurate number is about 11 and a half. So 11 and a half years is the solar cycle. That's how long it takes it to repeat back to a minimum. Okay. Now, the minimums are very reliable, right? So the sun almost always returns to having zero sunspots every 11.5 years. The maximums do vary, right? So that they almost appear to have a cycle themselves, right? Because they round up and back down. And in fact, that is about a 100-year cycle if we just look at this graph, which may have been what you're thinking about. So regardless, the numbers do not remain the same, right? So minimums are reliably zero, but the maximums can range anywhere between 100 sunspots up to over 300. And if we look at a greater history of data, back to 1600, when early astronomers first started, actually counting the number of sunspots, or a little bit later, around 1620 or 1610, then we can see that there's like this period called the Maunder minimum, where there was a very few sunspots, and then we see kind of this like 100-year cycle or so, but it's not exact. And maybe we're just not seeing enough data, or maybe there isn't a clear cycle, but maybe just some variation or a number of factors and a rather complicated, cycle on a greater time period. Okay, so more about the sun's magnetic field, which segues nicely from talking about the solar cycle because they are directly related to each other. The solar cycle is all about the magnetic field going through its own cycles. That's not totally different from our field. I said our field is so much cleaner, but it flips direction, right? But it also doesn't waver around too much between those flips. But every 100,000 years or so, there is a flip of our north and south poles. So we can think that the sun is just going through a sort of a flipping process, just much faster, right? Instead of thousands of years or hundreds of thousands of years, it's happening on the scale of just decades. And in fact, that idea of the flip is relevant because you're not responsible for this, but it's just an interesting detail, is that yes, it's 11.5 years to go from minimum to minimum, but the actual way that the sunspots are, the way that what is it, that they populate, the direction that they populate from, because they always start near the equator and then they fill in towards the poles, and then they do it in a reversing direction. So what is it? Because it basically is a north-south reversal. So it's really 22 years, or I guess 23 years to have the full cycle, although the difference between the two is just that one of the cycles is a mirror image of the other in terms of north and south. But I just mentioned that because I mentioned our own field flipping. So that's the idea that's happening at the sun, is it also, there's a flip involved, and also a lot of kind of chaotic processes in between. And that'll be a flip of the poles. This is just a summary of magnetism. We already covered this when we introduced magnetism before, which is why I'm skipping over it. What is left in here for reference? I remember that we compared the magnetic fields created by planets to the magnetic field created by a electromagnet, which is the name given to a magnetic field created by a current through a coil. This was the dynamo theory of magnetic fields created by terrestrial planets. Here is the flipping poles on Earth and the slow pole migration. All right. So when we look at the sun in UV light, we're actually able to see some of the field lines as they come out of the surface. And if you know what to look for, and I'll point it out again, but look right here. This looks like a magnetic field line. See? It's got that curve, another curve to both sides. It's not too different from our picture of the iron filings that grow around the poles of a magnet. So this really looks like a little field, a little, two-pole magnet showing up on the surface of the sun. And indeed, that is what we're seeing. In other words, we're seeing evidence of the magnetic field because the sun's surface in this spectrum, right? So looking at it in UV light, which of course is invisible light. So this would be an artificially colored image, just colored blue for reference, and because that's often chosen for UV light. But the actual light is not one that we could see with our eyes, and it's not actually blue, right? It's ultraviolet. And so, but it was taken with a sensor that can detect ultraviolet. And in doing so, we're actually seeing the light emission from iron particles. So we don't think about there being a lot of iron in the sun, but there absolutely is. Just like there's a few molecules, not many because of the hot conditions, but there's also not many of the heavier elements, but there are some. There absolutely have to be, because these are the same trace amounts of iron and heavier elements that we have, on the terrestrial planets. And this iron that is being kind of bubbled up and boiled at the surface is emitting, it's glowing at a particular wavelength, and it's creating an emission spectrum because it's atomic iron. So it's not acting like a black body. Instead, it's acting like a hot gas because it is essentially it's gaseous iron, right? It's like iron fumes, vaporized iron. And in that way, it has a particular wavelength that identifies it. The same way that I talked about, emission spectrum acts like a fingerprint of a gas. It tells you what that atom is. That's how we're able to use it to measure velocity with the Doppler effect, because we can identify what it would look like if it was at rest, because it's got those exact emission lines. Because remember, the emission spectrum is all black except for a few defined lines. And so here, that's what the UV is. It's that fingerprint of iron. And okay, that's all great. We can identify there's iron on the surface of the sun, which is interesting in its own right. But the better thing is that iron is so easily magnetized. That's a special property of iron. There are plenty of other metals that are easily magnetized, but iron particularly so. And that means that it's really going to readily follow the magnetic field lines. There you go. That means that when we take an image like this showing us iron, we're able to see the field lines. So kind of neat idea. There are other ways to see field lines as well. You can actually see them with a type of sensor that is directly detecting the magnetic field. So using sort of like a sort of imaging, imagine like a digital sensor, but instead of picking up photons, it's picking up the electromagnetic waves created, by a nearby magnetic field, and that's called a magnetogram. So it's a direct image of the magnetic field, and so it's showing. In this case, we're seeing. Zoom in a little bit. It's showing regions of the two poles. So probably, I think the color coding is almost certainly black for a north pole and white for a south pole, and so you can see essentially sunspots where you have those two side-by-side poles, which would create that magnetic field band that goes up out of the surface and back in. And then there's also, like other spots on the surface where you can see clear evidence of the magnetic field. And while we're talking about this, talking about ways to use either a particular wavelength of light or a special type of sensor, the magnetogram, to look at the magnetic field on the surface of the sun, we might as well talk about all the other ways that we can look at the surface of the sun. Not that all of them are related to the magnetic field, so this is a quick side idea, quick tangent. And it's just, and just really appreciating all the ways that the sun can be displayed, right? All the different faces of the sun, so to speak. There's the Dopplergram, which actually shows the surface movement. We have the visible light, so actually, exactly what it would look like to the naked eye, shown right here. And then we have a number of different wavelengths. So these are all going to be, light. So all electromagnetic filters or specialized cameras that just focus on one wavelength. And the wavelengths are in angstroms in this figure. And we haven't seen an angstrom before, but it's 10 to the negative 10. So when we look at this and we've got our angstrom, if I have 1700 angstroms, that's 170 nanometers. So if you want to convert each of these to nanometers, you would just divide by 10. So this one here would be 170 nanometers, okay? And so 170 nanometers is showing the ultraviolet in this case. So it's showing, because it's showing the shorter wavelength ultraviolet light, which is what this one shows. I'm not sure why it corresponds to 4,500 Kelvin. Not exactly. I wondered about that because I don't think of ultraviolet necessarily being related to 17 to this wavelength, or rather to this temperature, because this is a cooler temperature. So it's probably going to be something with emission rather than black body, although the temperature is given, so it's a little unclear. But it's really the only one that really kind of stands out as being an open question. I'm sure there's a good reason, but it's definitely ultraviolet light, artificially colored. You've got another one here, which I think is my favorite, which is showing 6,000 Kelvin. So, real close to that surface of the sun temperature of 5,800. And it's showing just the wavelength that corresponds to 6,000 Kelvin in the continuous black body spectrum. And so that's 4,500 angstroms, which is 450 nanometers. And so in other words, this represents basically the most probable photon that is released from the sun. So the most abundant photon that's released from the sun, and the color of that photon. So if you were to filter out everything from the rainbow except the very peak of that black body curve, this would be the color. And it really clearly shows that that color, the most probable color that the sun produces, is that green yellow color, which is kind of that fun statement to say that we have a green sun because that's the peak of its emissions. And this is kind of the shade of green, or the hue of green that the sun is. And as I could continue, there are more of them. I'll just summarize that we have some ones that are all going to be shorter wavelengths. So 304 is just 30 nanometers. So that's into the X-rays, right? So a lot of different X-ray emissions, and then all the way down to really high energy X-rays. In the case of this one here, because it corresponds to 6 million Kelvin, right? So some really hot gas. And notice that it says it's for flaring regions. So these are real hot spots on the surface, and they're going to be hot spots probably in the atmosphere, because remember, the surface is never going to get that hot, 6 million Kelvin, but the corona can. Okay, so back to the sun's chaotic magnetic field. The differential rotation that we mentioned before causes, so the result of that differential rotation is that the magnetic field lines deform, twist, and kink. Okay, so this is what I was talking about. If they started out very, perfectly aligned with the rotation axis, then over time they would get distorted, and that distortion would eventually end up causing these internal loops, these points where the magnetic field is folded back over on itself. All right, and that is when those magnetic field lines, once they twist, kink, and build up, they burst through the atmosphere and form pairs or clusters of sunspots. So some videos you can look at. Here's the idea I mentioned before, that the gas doesn't flow to the surface because of the magnetic field. That's what actually makes the sunspots cooler. So that when the magnetic field is coming right up out of the surface, the cooling is caused by the magnetic field's effect on convection. It prevents the convection from taking place fully, and that's what causes the cooling. So if we wanted, right, to look at a couple of sunspots here. So if the leading sunspot is the North Pole, what is the polarity of the trailing sunspot? So if this one is north, and you got a pair like this, what must be the polarity of the other one? Well, if you've been kind of following along, you know that they have to come in, you know, with two poles. They come as a pair. So it's not just, coincidence that you see sunspots in twos like this. So that means that the other one is going to be a south. So you have your north and south poles. So it's a pair of poles right there on the surface of the sun. The two sunspots represent that pair of poles. Okay, so the answer, of course, would have been south. All right, and how do we know? Well, I mean, we could, model this in a sense. We can look at its consequences, but there's a way to almost directly see that we are looking at a magnetic field. And you already saw, like, the magnetogram and other ways. But historically, this was the first way that we were able to confirm that a magnetic field existed based off of how the light behaved. And so it's a kind of a famous result, and it's called the Zeeman effect. This, by the way, is what the field lines would look like. I mentioned this before. I said they arc up out of the surface. So they almost look like a U-shaped magnet. Okay. So to experimentally confirm that these really are related to magnetic fields. So in other words, to confirm that the sunspots have stronger magnetic fields than the surrounding areas, and thereby say, yeah, it is the magnetic field that's causing the sunspot, right? And then, building on that theory to say exactly why, and then coming to the conclusion that the magnetic fields are what prevent the convection and thus the cooling, and that's why the sunspots are dark. All of that starts with a confirmation like this, okay? And what we look for is in the surface, in the light that comes from the sunspot, so the light that's coming out of the sunspot, streaming away in every direction. Well, when you analyze that light and you split it into its different wavelengths with some prism or other splitting technique in a laboratory on Earth after you've picked up that light with a telescope, you notice something that indicates the atomic structure. And this effect, the Zeeman effect, relates to energy levels, ideas that we've talked about before with atoms. And let me quickly review. So orbits, also known as energy levels of electrons, okay, are like steps on a ladder. Electrons move up and down the levels. This is the idea that we've talked about a lot when we talked about the difference between emission and absorption spectra, right? An emission spectrum is all about excited electrons on one of these higher rungs falling back down to a lower rung and releasing light. That's what emission is. Absorption is a electron already at the bottom of the ladder and getting excited up to a higher rung, and thereby taking the light out and creating that absorption spectrum, because those correspond to the missing bands of light in an otherwise complete rainbow. So the Zeeman effect is about splitting of the atomic energy levels. So instead of just having one rung on the ladder, when you take that same atom with its same energy levels, because remember, those energy levels are like a fingerprint. They correspond to that element and none other. And specifically the isotope. So, like hydrogen has a particular emission spectrum, deuterium has a slightly different emission spectrum. Very similar, but measurably different. So every single isotope, so every combination of proton and neutron has its own spectrum, its own spaced rungs on the ladder. And it's not by accident that they showed the rungs, spaced in a strange way. This ladder is purposely lopsided because that's the way energy levels are. They're not evenly spaced. And when we look at different atoms and their emissions, the biggest difference is going to be between actual elements. So when the proton number changes, changing the neutron number only causes subtle changes. But an even more subtle change is the one we're talking about here, which is taking that individual energy level and causing a very small split so that now that energy level is split into two separate energy levels. So every rung of the ladder is now split into two. It's showing the original rung, but we only care about the two that are to either side of it. So now we have a spectrum that looks like this instead. So we have every one of the emission bands is now a pair of emission bands. And so in this case, we could see a overlay of the original signal and the magnetically affected one, because inevitably there's going to be, even in a strong magnetic field, you're going to see both. You're going to see, because there's going to be some atoms that are experiencing the full effect of the magnetic field and have the split, and then others that don't. So it always ends up being sets of three because of the not being able to just look at a single atom. So the splitting of the atomic energy levels when there's a magnetic field has this characteristic look to the emission spectrum. So this is how, by just observing the emission spectrum right here, that scientists are able to say, okay, this is the type of spectrum that comes from a location where there's a strong magnetic field. Full stop. All right. And the splitting can actually get more complicated than that, depending on what type of energy level it is, and so on. Okay, so the sunspot polarity. So the leading and trailing polarity is opposite in the northern and southern hemispheres. This is what I was trying to remember. And so the leading and trailing polarity flips every 11 years. All right. So the sunspot number, right, counts up and counts down, and then the polarity switches every 11 years. So the full cycle is two of those 11-year cycles, or about 22 years. And they're rounding 11.5 to 11. It's usually presented as 11.5. I believe it actually is in the text. But rounding it to 11 is fine as well. I would never ask you to, say, is it 11 or 11.5? Both are fine. And so what else takes 11 years? The light to get to the Earth, the sun to rotate once, the solar minimum maximum cycle, this astronomy lecture. Well, you probably know it's this one right here, the solar minimum maximum, right? So, because I was just saying that it's, that's the max. Go from min to min is 11 years. And after you have done one full start of the solar minimum, so minimum number of sunspots, return to a minimum number of sunspots, well, then you switch the polarity and do it all over again. Okay, so that's why you double it to kind of come up with that 22-year cycle. So most people actually will refer to the 11-year cycle for the solar cycle, but technically it's 22 years. Yeah, it's the best way to think about it. And just remember that the 22, really has these two almost identical looking peaks to them. And the only difference is that polarity, because the abundance doesn't significantly change. So how are these magnetic effects of the sun related to solar activity? Well, they cause all kinds of interesting named uh, solar events, and we're going to run through some of them. And then focus on just the most important ones. I'll call attention to them. Plages, a term you're responsible for. They refer to bright clouds and warm regions near sunspots. So they're particular hot spots on or just above the photosphere. Prominence is a surface feature on the sun where the magnetic field line is really prominently shown because it has a trail of plasma that's really following the field line. So there would be a sunspot at each of these points, right? One north and one south pole, because these are the field lines, of course. Right, so enormous thick loops of gas attached to the surface of the sun. All right. They've been, since you can see them with naked eye observation, their existence was known well before the invention of the telescope. Although I wonder how long these people were staring at the sun, right? Um, hopefully used a reflection or something. And so the name, flame-like tongues of live embers coming out of the surface. They're huge, right? But that's not a big surprise because remember that the sun is 100 Earths across. You'd have to line up 100 Earths to actually cover the diameter of the sun. And so, this is the kind of size we'd expect for such a large body as the sun for surface features. Here's a bunch of ones that are just kind of thrown in here. Spicules, filaments, faculae, coronal loops, helmet streamers. So all these different names of different surface features. You are not responsible for all these ones. But a couple ones that are really important, solar flares and something called CMEs, which stands for coronal mass ejections. So these are the two most high energy um, solar events that occur within that framework of solar activity and are created because of magnetic field, changes of the sun. Solar flares are sudden bursts of X-rays when a magnetic field suddenly snaps and reorganizes. So the huge amount of energy associated with a magnetic field rapidly changing is represented by a solar flare, a burst of X-rays. So shown in this artificially colored image, the really bright, washed out part of the image is a high concentration of X-rays. The whole image shows X-rays, right? Obviously not their true color, right? But assigned, some sort of idea that the darker regions are fewer X-rays, and as they get lighter and oranger, and that represents more X-rays, up to probably purple being, just under the maximum, and white being the maximum concentration of X-rays. And then coronal mass ejections are not bursts of X-rays, but instead bursts of particles. So one of them is light, solar flare. The other is mass, matter. And the particles are protons and electrons, the solar wind. So a coronal mass ejection is essentially a gust in the solar wind. This is kind of a fair way to think about it. It's a big uptick in the strength and density of the solar wind. So it's a big burst of particles that accelerates away from the sun, and essentially it's a huge chunk of the sun's atmosphere that gets accelerated away from the sun so that it escapes the sun's gravitational pull. So it takes off like a rocket and is able to just head off into space and then wash over planets if they happen to be in the way. Some videos to take a look at. Coronal holes are windows in the corona where the magnetic field lines extend down into space. So it's when the field lines line up with our sort of like direction of view. And so when we look into a coronal hole, we're able to look right through the corona and see down into, or right down the field lines into the surface. So it'd almost be like if you could look down above the North Pole of Earth and down through where the auroras are caused, then that would be the view. So what do these mean for planets like Earth? So solar wind and coronal mass ejections send charged particles to Earth. We always are getting bathed in the solar wind, which is kind of the baseline flow of particles, not light, because obviously we're also getting bathed in light. But we also have a steady amount of protons and electrons washing over our planet. We know that these charged particles are redirected by our magnetic field and cause auroras at the poles. The light coming from the sun is not affected by any magnetic field, including ours. So that's an important thing to remember. Solar wind, since it's charged particles, is affected by planetary magnetic fields. Light, including X-rays, are not. They can be affected by gas, right? They can be absorbed in our atmosphere, and they are, right? But they're not affected by our magnetic field. Here's an example of a aurora up in the north, with the name called the Dragon Aurora because it kind of looks like one. Seeing it from space, as we saw back in the Earth chapter, looking at a aurora on Saturn. We haven't seen an image of this yet. One in Eugene, because I think one of the authors of the slides must come from there, because it's the second time we've seen that city. And so quick summary about what this means for interference on technology. So these big events, these solar events, right? When we say that the solar activity is at a maximum, or people talk about a solar storm, they're talking about some combination of a coronal mass ejection, or potentially, a solar flare. Solar flare kind of matters more if you're in space, because otherwise it's not going to affect us, because the solar flare is just the uptick in X-rays. So the X-rays are never going to make it through our atmosphere, but they can cause our atmosphere to swell in size, because more X-ray absorption means more heat in the atmosphere. And they also matter for satellites that are not protected from those incoming X-rays. They'd also matter for any sort of like mission to the moon or Mars or other unprotected locations. But solar, or rather coronal mass ejections, have more direct impact on the surface, because they can follow those field lines down to the poles and essentially cause a otherwise harmless aurora to be strong enough to cause some disruption. And I'm not talking about hurting humans directly, but rather messing with our, in 1921, the telegraph equipment, right? So back then they would have telegraph lines, and more recently, causing some unintentional detonations of basically like kind of radio controlled mines. And then also in the late 80s, causing major blackouts, because the grid kind of acted like an antenna that picked up the emissions from this high powered aurora, this high powered coronal mass ejection coming down along our field lines. So this is kind of summarizing the sun and its influence, the way it can damage spacecraft because they're not protected by the atmosphere, right? So solar flare photons, those X-rays I was talking about, definitely matter for satellites. They matter for the International Space Station. It's actually a major thing, health risk that has to be considered and accounted for. But once you get down into the atmosphere, the main thing to think about is how the effect can cause sort of a induced signal. So what's happening with those ionized particles in the atmosphere and the ionospheric currents, right? The way that that solar wind is creating a current in our atmosphere, and how that current can then interact. So the geomagnetically induced current in power systems, right? So you have solar wind induces a current in the atmosphere. That current induces a current in our power system, because that's the way that electromagnetism works. You can just have induction, induction, induction. And indeed, that was what caused that blackout up in Canada. All right. So the last reason we want to study the sun is because space weather can affect us. And so we need to be able to monitor it and predict it, and make sure that we are prepared, especially if we're traveling into space, or maybe traveling into space and spending greater amounts of time in space in the future, or hoping to colonize Mars or something. All right, so we're going to wrap this one up. Let me stop the recording.